morning, good afternoon, and good evening. And I know, conscious of the time, we are at the end of the day, different time zones. So thank you for the invitation. Pleasure to be here. Um, my talk will have a different coverage. So I'll be focused more on the commercial opportunities, the commercial status, um, some of the trends and some of the challenges of exploiting optical fibers and fiber sensors for industrial applications in different segments. So first, I'll draw a contrast to the existing industrial sensing market and how much of that is fiber optic sensors, and then draw some conclusions of why would it be valuable and necessary to use optical fiber sensors for a variety of industrial sensing applications. I'll illustrate some examples that may be somewhat repetitive to what previous speakers have mentioned, and then I'll give my take on where I see potential future opportunities, and we'll wrap it up. So, present commercial status. If you look at the global market for sensors in general, um, different marketing agencies like BCC will tell you that by 2026 it's roughly 250 billion with a B dollars a year. And obviously, this is segmented across different industries, application segments. But as you can see in the graph here in the pie chart, by far the largest one, obviously and intuitively, should be industrial sensing with roughly 37%. So as you can see, there is at least $30 billion annually of expenditures related to industrial sensing. And sadly, fiber optic sensors don't make a significant dent out of these $30 billion. So there is an incredibly large market that is not fully tapped, and this is a nice opportunity for fiber optic sensors and photonic sensors in general to exploit that market. If we break it down into more detail, just the industrial segment of this global sensors market, obviously it has its own sub segmentation into, true manufacturing, process control, automation, and then the usual segments that we are more familiar with for fiber sensors like oil and gas, energy and power, and to some extent chemical and mining. So you see here the segmentation. So roughly right now we are sitting at 20-some billion dollars, but it's expected that we'll reach around 50 billion by 2030. Now, in terms of which parameters are the most popular, you can see here in the pie chart that obviously temperature, pressure, and force, strain, torque are some of the three top parameters that will be the most popular. But there is a broad variety of different physical and chemical sensors that are needed for a broad variety of applications in sensing. And again, just to draw the contrast of how poor the penetration is in industrial sensing of fiber optic sensors, we can look at the breakdown of strain gauge sensing technology. This report is dated. It's from 2007 by Frost and Sullivan. And at that time, they were estimating that the global market for strain sensing equipment was on the order of $3 billion. And out of that, only 3% or 100 million were being supported by optical and fiber optic sensing solution. So the sky is the limit. There's obviously a lot of market share that can be gained by fiber optic sensors. It's just a matter of having the right solutions at the right price point and with the right features. And fiber optics has demonstrated that this is very achievable, and fiber optic sensors have had significant milestones and success stories across different application fields, whether it's fiber optic gyros, high current, high sensing in the electric utility industry. And one of the case studies that it's been more significant, more popular over the last 20 years has been the strong adoption of fiber optic sensing in the oil and gas industry. So this market peaked around 2014. At the time, there was a global business of $400 million among specialty fibers, specialty cables, downhole sensors, distributed sensing, connectors, etc. And these got to be very pervasive across the oil industry. Thousands of permanent downhole installations, hundreds of thousands of DTS, and more recently, the surveys. So if we were able to do it for a really harsh, really challenging industry like the oil and gas, certainly we can do the same for a variety of opportunities in the industrial sector. So traditionally, fiber optic sensors have run the gamut of a variety of different applications. Mentioned oil and gas. Previous speakers talk about wind turbine blade monitoring. Obviously, there is lots of opportunities in aerospace, like the overheat detection in civil aircraft that Proximion talked about. The defense sector has also been attractive for fiber solutions, not to mention structural health monitoring, transportation, biomedical applications. But if we really look at what is the true segmentation and the true commercial reality, as you can see here for the case of single point type sensors, whether they are FBG, Fabry-Perot, or any other type of fiber sensing technology, about 9–10% of the total global market is for industrial applications. So there's still a lot of room to growth. Most of the single point market is dominated by fiber optic gyros. It's over $500,000 to $700 million a year market globally, gyros, and everything else is fairly segmented. But you can see here that the trends are changing, whereas in 2015, oil and gas and some other applications like civil structure monitoring were dominant. Nowadays, some of those markets are shrinking. Technologies have already been developed and adopted, and there is an interest to grow both the biomedical sector as well as the industrial one. So we see here there is some growth, but I expect that as the other applications come and go, people will start paying more attention to industrial applications and develop new solutions. The same can be said of the distributed sensing side of the industry. DTS, DAS, DSS solutions for a variety of applications. Again, historically, this has been dominated by the oil and gas sector, some defense, security monitoring applications. And sadly, the industrial side remains very, very small compared to the rest of the solutions. The same is true for the more recent and hot market of distributed acoustic sensing DAS. You see that some of the preferred applications revolve around transportation, security, seismic mining, monitoring, carbon sequestration, but very little related to process control, industrial sensing. So even though these segments are relatively small, it also intrinsically implies that there is a lot of room for growth, a lot of room for opportunity. And in a way, there's been a unique and really outstanding success story of fiber optic sensors in the industrial segment. And this one is a Canadian company called Photon Control. Whether by design or by accident, they ended up identifying the killer application, the killer app, and that basically revolves around doing temperature sensing of the support chocks for plasma etchers in semiconductor wafer manufacturing equipment. The technology is based on phosphorescent temperature sensor probes with very simple PLC type readout detectors. This company was acquired back in 2021. It has been the single largest acquisition of any fiber optic sensing company at $387 million. And prior to their acquisition, they had revenues on the order of $60 million a year Canadian. Over here, you can see historically some of the most significant acquisitions of companies in the fiber optic sensing space, and not even the acquisition of OpSense in 2023 at $250 million comes close to the 387. So if you identify the right application where fiber optics makes the most perfect sense, you not only can make a lot of money, but you could be the target of a nice acquisition. So why industrial sensing? Well, the reality is that if you look at any manufacturing plant, if you look at the fabrication of any specific product, whether it's in a heavy industry, food industry, pharmaceutical, textiles, materials, etc., you have an incredible amount of sensing and monitoring to do to perform control, to ensure safety of processes of personnel, to carry out predictive maintenance of the equipment, the infrastructure, also to have a more energy efficient production and reduce your costs, and certainly for quality control. So sensors by themselves are very pervasive across the industrial segment, and there is a need for a broad variety of different sensors, from temperature to pressure to strain, load, position, gas, humidity, presence, you name it. And this is such a large commercial opportunity that obviously there is a large pre-existing ecosystem of suppliers, vendors, developers, system integrators, and you'll obviously recognize a lot of the names here. So on one hand, we have our work cut off for us because there is obviously well-established players that have broad portfolio of conventional electronic or electromechanical sensors. And as you can see here, there is a broad variety of different types of sensors. But that is not to say that fiber optics cannot do it. You see here on the upper corner a broad set of different types of temperature and strain sensing FPG sensors. So the trick here is to identify for your given company, your given process, your given technology, what would make the most sense that you can do with your own solutions based on fiber optics versus the specific needs and technical requirements of that industry. The other key trend here to recognize is that more and more we are seeing the convergence of the so-called Industry 4.0, which is a blend of sensing, monitoring, control with artificial intelligence tools, with a lot of data analytics, with robotics, smart automation. And obviously, a key ingredient in all of this, the eyes, ears, fingers of any process are sensors. So one way or the other, sensors will be required. It's just a question of how can fiber optic sensors play within the envisioned environments of an Industry 4.0. And the answer is very simple. When you visit a factory, if you know about process control or automation control, sensing in an industrial setting, you'll quickly realize that everything revolves around PLCs, programmable logic controllers. So a lot of the ovens, valves, switchers, anything and everything that is done in an industrial setting is directly or indirectly monitored, controlled through a PLC and an SCADA type environment. So the trick is make our fiber optic instrumentation seamless with this type of system. And locally, some companies have had that vision. They had identified these needs. And one of the very first products to address this was the distributed temperature system by Yokogawa, the DTSX, back around 2010, where they developed a Raman DTS system that was fully PLC based. So every building block of the system, whether it's the main controller, the multi-channel unit, the power supply, the processing unit, are all separate PLC pluggable piece of modules that then can easily interface through the software that they developed into any industrial PLC environment. Another similar example is the MESCO FBG hotspot temperature monitoring system for power transformers. This is technology developed by HBK in Portugal. And here you see the three key building blocks. Again, it's a PLC-based system interrogating FBG temperature sensors, but all the data is processed and seamlessly transferred to the rest of the electric utility SCADA system through this instrumentation. And finally, there are new players, there are companies that are also keeping an eye out for these ideas. More recently, last September, you have the announcement of Photon First in the Netherlands and Gartner Instruments that they are collaborating together to basically make the FPG-based interrogators of Photon First be seamless with this PLC and Profibus EtherCAT type of industrial SCADA system. So obviously, you see that little by little we are heading that way. Now, what are the actual applications, the actual opportunities for industrial sensing for fiber optic sensors? I have identified several areas. This is by far not complete, but these are some of the areas that are easier to reach, the most popular, the most common. So on one hand, again, process control. You need sensors for temperature, pressure, level, flow, force, strain, torque, you name it. So any type of conventional sensor, you can, for harsh environment applications, for multi-point sensing opportunities, you can try to develop your own fiber optic equivalents. Earlier, Proximion talked about their solution for heavy industries, steel casting, forging, rolling, all sorts of heating, melting, and annealing furnaces. The same is true for the glass industry, all the fabrication of wine bottles, soda bottles, containers. The glass industry is also very high temperature intensive and requires a lot of temperature monitoring and control. And a broad variety of other industrial processes, one way or the other, are supported by furnaces, oven, boilers that require temperature monitoring and control. If you visit any chemical, petrochemical plant, you'll see that there is a need for a lot of tank level monitoring, detection of fugitive emissions of gases or liquids, monitoring of cracking columns, pipes, manifolds, etc. And then some areas that are not as well known, but there is tremendous opportunity is in asset condition monitoring of rotating machines, of opening and closing devices, conveyor belts, ball bearings, fire detection, and certainly electrical utility system. Evangelos presented some of the sensors that have already for many years been adopted inside power transformers, power generators. And then finally, another area that indirectly can be very nicely supported by fiber sensors is spectroscopy, gas, liquid sensing, environmental monitoring, monitoring of emissions from factory flue stacks, etc. So in some of the heavy industries, in the petrochemical industries, there is a lot of distillation and cracking columns. It becomes necessary to know the temperature profile, to control temperatures in specific points, to avoid overheating, to detect blockages, to avoid potential fires. Some solutions are already commercially available for some of these applications, like Siemens has the Cytrans TO500 system, which is based on an array of FPGs protected in a metal tube that can basically be installed along these boilers, tanks, manifolds. Earlier, Proximion talked about their solution for the heavy industry, the steel industry, where you can have different types of steel processing, whether it's casting, rolling, folding. And there, obviously, there is a need to properly control the temperature across the process to ensure the proper um, uh, annealing, the proper solidifying of the materials so that the metallurgy of the final composition is correct, and you get the right quality type of cast metal. One area that, again, I think is completely unexploited at the moment is that of condition monitoring, particularly through acoustic sensing. This is very typical, very common, used in piezoelectric and other acoustic sensing devices. And the idea is that you can, over time, monitor any piece of moving, rotating, vibrating piece of equipment by listening to their specific acoustic signatures and how they change over time. And that's a way to determine how close is a specific component, a specific piece of equipment, close to needing maintenance or close to a potential failure, or even close to causing a catastrophic accident, catching on fire, exploding, breaking other pieces of hardware. So as you can see here in the graph, depending on the type of piece of equipment, it typically may be rotating, it may be vibrating, and producing certain acoustic emission spectrum. And if you have the right acoustic sensing fibers, fiber-based microphones, or even a distributed acoustic sensing system based on coherent Rayleigh, you can continuously and over time monitor a variety of pieces of equipment like large power electric motors and determine whether any of the ball bearings, couplings, rotators, stators are displaying any particular problems and basically do corrective maintenance. This has been demonstrated both experimentally using, again, fiber optic distributed acoustic sensing, and with control experiments where you have rollers from conveyor belts in comparing the acoustic emissions from a new one from a heavily damaged one. Same is true from real installations in the mining industry, other heavy industries where you can monitor in real time long lengths of conveyor belts, either with DTS or DAS solutions, by running the cables underneath the support structures and looking for areas of overheat or intense acoustic signals that will pinpoint which specific rollers are not rolling, are getting stuck, or need replacing. Other unique applications of acoustic sensing, for instance, could be applied to air conditioning systems in large factories or even commercial buildings. So if you have problems with the compressor, if you have problems with the cooling fans, etc., you can monitor all of that infrastructure with a continuous fiber optic cable that will pinpoint exactly where there may be some problems, and the maintenance engineers can go and fix that. So lots of opportunities here. Certainly what the industry demands, not only for industrial applications, but all sensing applications in general, is both sensors and instrumentation that are relatively low cost. Distributed sensing has become very pervasive across the industry with DTS, the distributed strain sensing, as well as distributed acoustic sensing. But now for some of the industrial applications, more and more there will be a need for distributed pressure sensing, DPS instrumentation, as well as distributed chemical sensing to detect hydrogen, detect hydrogen sulfide, other pollutants, detect methane for long length distribution pipelines. I think historically the fiber optic sensing industry has overlooked the food and the pharmaceutical industries. Lots of opportunities there for sensing for process plant control. And certainly several companies have already made inroads into heavy industries, but there is a lot more to be done, lots of opportunities there. And we cannot overlook opportunities brought on by green technologies, environmental sensing, pollution detection, etc., mostly centered around gas sensing solutions. One key thing not to overlook for industrial applications is that oftentimes these involve harsh environments. There's lots of dust, water, high temperatures. So the fibers, the cables, the specific sensors need to be high temperature resistant. They need to use the right protective coatings, whether they are metal coated fibers, ceramic coatings, protective sheets, and certainly the connectors, the rest of the packaging of the instrumentation needs to be rugged to survive long term in these environments. And as I mentioned earlier, one way or the other, whatever is done in an industrial setting will need to be a part of the rest of the SCADA system of that plant, the supervisory control and data analysis system of that. So we need to figure out how to extract data from our fiber optic instrumentation and make it seamless into these SCADA systems. And that also involves making things simple to run, plug and play, as opposed to needing a PhD in optics or electronics to figure out how to calibrate the sensors, how to enter data into the software provided by the vendor, and get everything up and running. And of course, prices remain relatively high compared to conventional technology. So there's got to be a cost reduction effort here. So in summary, there is at least $30 billion a year in industrial sensing, and this is expected to grow to 50 billion by 2030. So large market opportunity. It's in my personal opinion, very untapped by fiber optic sensors. So the sky's the limit to what we could do for industrial sensing. And sensors, fiber optic sensors themselves lend themselves very nicely for opportunities in this sector by their unique features for multi-point sensing, multi-parameter sensing, distributed sensing, their intrinsic safety and immunity to electromagnetic radio frequencies. So these are the key characteristics that would beat the conventional electronic sensors. However, again, we need to make the devices rugged, seamless with the SCADA systems, and certainly the cost. I mean, some sensors can be a factor of 2 to 5 times more expensive than a conventional electronic version. So I appreciate your attention and staying late in European time, and thank you, and enjoy the rest of the day, and happy to answer any questions. So.
Great.